You are not running the equation to check if it is right. You only have to match. Somebody left that comment on my last video, and it is the reason this one exists. Last time, a viewer sent me a formula, he says, cracks the hardest unsolved problem in maths. I tested it, I made a video about it, and then he replied with something much better. He said, the answers are already decided before you start. So you never have to calculate anything. You only have to match. Then he gave me a list of numbers and one claim I could not ignore. The claim was 99% of every number gone without working out a single path. So I built his method, all of it, and it surprised me twice. Quick reminder of the problem because it fits in one line. Take any whole number. If it is even, cut it in half. If it is odd, triple it and add 1. Then keep going. Forever. Start at 13 and it wanders for a while and it ends up at 1. Every number anyone has ever tried ends up at 1. Nobody has ever been able to prove that they all do. Here is the piece of arithmetic his whole idea is built on. Follow an odd number all the way down and count 2 things on the way. Count how many times you tripled it. I am going to call that the step count. Count how many times you halved it, that is the halvings. Now take 3 to the power of the step count and multiply it by your number. You land just short of a power of 2 every time. The gap you land short by is what he calls x. So the whole journey of a number becomes one line of arithmetic. And this is his real insight, so it is worth slowing down for. X is not random, and it does not depend on the number you started with. It is built only from the halvings you did along the way, which means you can take x apart and get those halvings back. Subtract the biggest power of 3 hiding inside it. Count how many 2's divide what is left. That is your first halving. Then do the same thing again, one size smaller. He calls this peeling, and I want to be clear about something. I ran it on every odd number below 4000. It recovered the correct path every single time. 0 failures. So let me actually use his formula on a real number. Take 13 and guess that it needs 2 odd steps. Add 2 steps. Only certain values of x are even possible. The smallest one is 5 and the rest are all 3 plus a power of 2. Now we test. 9 times 13 is 117. Subtract that from a power of 2 and see what is left. With 4 halvings and with 5 and with 6, the answer comes out negative. At 7 halvings, the answer is 11. And 11 is on the list. So 13 takes 2 odd steps and 7 halvings. We never followed 13 anywhere. We just looked it up. Then there are his lists. And this is the part that made me take him seriously. He posted 16 numbers that take 2 odd steps and 33 that take 3. I generated both of them from scratch without looking at his. Every single number he posted is correct. The second list is not just correct, it is complete. All 33 of them in order, nothing missing. The first list misses exactly one number, and that number is 3. He also said there are 999 of them at one odd step. I counted there are 999. This is not somebody guessing. So I wrote his method out as a program, exactly as described. Try a number of halvings, work out the step count from the size and peel. Stop when it fits. There is no trajectory anywhere in the code. It got 27 right at 41 odd steps. It got 871 right at 65. It got a number in the 60 millions right at 357. His method works. That is the first surprise. Here is the second one. I timed his method against the boring way on the same numbers. The boring way is just doing what the problem says, one step at a time. On a 20-digit number, his method takes over 100 times longer. On an 80-digit number, over 400 times longer. The last video ended on a 240-digit number. The boring way finishes that one in 6/10 of a millisecond. His method needs nearly a full second. Same answer, more than 1,000 times the work. And the gap gets wider with every digit you add. If this is your kind of thing, subscribe, because the strangest part is next. Because none of that was his actual claim. His claim was that a step count of 5 wipes out 99% of everything, up to a ceiling of 2 to the power of 2000. And this one you can settle exactly on paper. A number with 5 odd steps is completely decided by its 5 halvings. So counting those numbers is only counting the ways to choose them. Below his ceiling, the total comes to 10 to the power of 14. That is 100 trillion numbers, which sounds like a lot. But his range holds about 10 to the power of 601. So a step count of 5 does not remove 99% of them. It removes one part in 10 to the power of 587. And you can watch that happen in a range small enough to check by hand. Under 1,000, 11% of numbers finish in 5 odd steps. Under 10,000, under 3%. Under 200,000, a third of 1%, and still falling. Here is why it goes the wrong way. Every odd step only shrinks your number by about a quarter. So a bigger number does not need a few more steps. It needs proportionally more, all the way up. I took real random numbers and counted the steps. At 10 digits, about 80 odd steps. At 60 digits, about 500. At 240 digits, about 2000. And at his ceiling, about 4,800. That is the step count you would actually need. A step count of 5 is not the bottom of the pile. It is a sliver at the very edge of it. None of which makes his formula useless. I want to be fair here. Run it the other way around, and it is genuinely lovely. Choose any path you like in advance. The formula hands you a number that follows it exactly. You cannot predict the wave, but you can build one to order. So where does that leave the comment? The lists were right. The peeling is real. The method works. It is a nice piece of mathematics found by somebody doing it for the love of it. It just is not a shortcut because it does the same work in a harder order. So thank you for the comment. This was genuinely fun to check. And if you can make the matching beat the walking, I will make that video too.